So this paper is one of the ones that's really great. I really, really think that this paper is fantastic. This is the stable rank filtration on K-theory paper. And I spent a lot of time thinking about it. It has a lot of really cool math in it. So now it sounds like I'm kissing up, but I really do mean it. It's a great paper. You should read it. But I'm going to be talking about something slightly simpler than everything that's done in that paper. And in particular, instead of working with general Waldhausen categories, I'm just going to talk about convenient addition categories, which are called because addition is convenient. So in particular, they are symmetric monoidal. That's the addition. But if you have symmetric monoidal, often you don't have a lot of control about what else is going on in the category. So what makes these categories convenient is that you have a lot of control about what else is going on. So first off, the zero object is initial. And all morphisms are monic. It's like all of my math recently has been only in categories where every morphism is monic, and at some point I'm going to figure out why these are the correct obviously the correct categories to work in. But so far, every time it comes up, I'm surprised that, oh, just restricting to monomorphisms makes my life so much better. And then the other thing, I want two things. I want the addition to behave kind of like a coproduct, but I don't actually want to work in categories that have a coproduct or where it is a coproduct. So all I really want is, so we have a map from A into A plus B, because we can, A is the same as A plus 0 and B is initial, so there's this natural map. So we have these two maps from A into A plus B and from B into A plus B. And what I want is that this morphism, so whatever this is, I give any morphism from A plus B to C, this is uniquely determined. Uniquely determined by these two morphisms. So a coproduct says, well, whatever two morphisms from A and B to C you give, this morphism exists. That's far too strong a condition for me. I just want it to be the case that if I have such a morphism, it's uniquely determined by the previous two. So the plus is kind of like a coproduct, but it doesn't have to be. And then the last thing that I want is that these two objects sitting inside this sum are disjoint. And I'm just going to write this as the pullback of A and B along these morphisms is 0. So because everything is monic, you can sort of think of pullbacks as intersections, and this is saying that their intersection is 0. So several examples, just so that you understand the kinds of things I'm working with. Finite sets are a convenient addition category where you take the injections, so not all morphisms, just in the injections, and then the 0 object is the empty set, and sum is the disjoint union. We can take modules over a ring or free modules over a ring if you want, and then direct sum is direct sum. And the 0 object is the 0 module. And then I'm going to want inner product spaces over some field K, which is ordered and square root closed, given that I want nice inner product properties. And then this doesn't have a coproduct anymore, because you can pick A and B to be sitting inside C in a non-orthogonal way, but the direct sum gives you an orthogonal sum. So this is really one of the examples that made me think about this a lot. And well, this is a symmetric monoidal category, so it has a K-theory. I'll discuss the construction of this K-theory in a minute, but it has a K-theory spectrum. And we can ask, what is it? And I want to take a minute here and talk about why I care about this, given that the first two examples are already Waldhausen categories and kind of exact categories, and why am I even introducing this example? And not everybody here has heard me speak about scissors congruence, but I talk about scissors congruence a lot. And in particular, it's these groups that classify which objects you can polyhedra, say, that you can cut apart and rearrange into other ones, and I think these groups are really interesting. And in general, these are related to the homology groups of, let's do the Euclidean ones. This is the Euclidean isometry group with coefficients in a Steinberg module thing twisted. So these are the, it's a free abelian group on, say, closed polygons, if you want, but that you're not allowed to move around at all. You're just allowed to cut them up into pieces. So this is one of the ways of doing this. And the twist says that this acts on this via the determinant. Well, with a twist by the determinant. And if you want to do spherical scissors congruence, so now we're doing polyhedra on a sphere, these are O and plus 1, I guess. And then you can do a similar Steinberg module where now you take polyhedra on a sphere and you're allowed to cut them up, but you're not allowed to move them around. And these are the scissors congruence groups are related to these. And these groups are really mysterious and they don't really come up in good ways. They're really, really hard to compute with. Most of the time we only care about H0 and we already don't know what it is past dimension like 4. So these are really, really hard to work with. And so a lot of the way that people work with it is by trying to relate them to other problems and at least seeing like what kinds of things can these connect. So I think about these a lot. But if you just mess around with these a little bit, you can replace this with GLN and a Steinberg module like this without a twist. And then these are groups that appear in Quillen's rank filtration on K-theory. And it actually makes sense that this should be a rank filtration because if you're cutting apart, say, polyhedra of dimension 3, you're ignoring the two-dimensional places where you cut. If I cut a polyhedron into two polyhedra, I sort of ignore the fact that I have sort of, when I put them back together, I have a doubled face there in the middle. And in fact, if you don't, there's a grading on this multi-dimensional scissors congruence group, and the filtered components are exactly these groups. And so it makes sense that, okay, these should be appearing as as associated gradeds to something. And now these start to look quite similar. In fact, these are the same group, which is one of the reasons I keep looking at them, because these are actually the same group. And so the differences between them are one of them is orthogonal groups, and one of them has a twist, and the other one has no twist and uses general linear groups. And so one of the things that I've been trying to figure out is what can I say about the other two groups in this series, which are the homology of O, I guess I'm using n+1, without a twist, and the homology of GLN with a twist. And this one, the one with GLN with a twist, I have no idea. Anybody wants to talk to me about these groups, would be thrilled to discuss these because I want to understand them and I don't at all. So this one, big mystery. This one right here, if you do the same thing, so what does Quillen do? He takes BGLR, does the plus construction, takes that space. You can do the same thing to the orthogonal groups. You can do the whole thing, take the plus construction, and filter it by dimension, and it gives you the same, these groups pop up quite naturally when you do the dimension filtration in Quillen's version of K-theory. For orthogonal groups. And so for us, like, oh, great, I just need to go find people who do orthogonal K-theory, and then, they'll be able to tell me stuff. And then I started looking for people who do orthogonal K-theory. By the way, if you know anybody who does orthogonal K-theory, please tell me, because all the people I talked to were like, no, you're looking at the wrong orthogonal group. You should be looking at ONN. And I'm like, no, absolutely not. That is a very different question and a far scarier one, and thank you, I'll stick to the ones that I can visualize. And they're like, okay, well, then you need to work over an algebraically closed field. And I'm like, no, I want to work over the real numbers. And then people are like, well, why are you doing that? Well, because it's scissors congruence, and that's what we do. So I was really trying to figure out what can I say about this, and the answer is me, I can't say anything about it. I can't compute with anything. But I was trying to learn what I can learn about rank filtrations, and Rognes's paper on the stable rank filtration is really cool, and I wanted to know, can I do a similar one for orthogonal K-theory? Can I give similarly cool, interesting results about orthogonal K-theory? So that's what this talk is about, and I'm including all three of these because my results are less cool than Rognes's because they, well, you'll see, because the spectral sequence is less fine. But I get different results in the case of standard K-theory that ought to give the same answer, but we don't yet have a proof of it. And I wanted to be able to give you both examples. So this is the framework. How do we construct the K-theory? So you can do this with a gamma space. I'm going to ignore all the gamma spaciness, but everything that I say, if you're more comfortable with gamma spaces, you can easily soup it up to a gamma space. So we're going to define a construction also, again, this kind of thing. If you've seen it with a different name, please tell me. I'm calling it the U dot construction because T dot was already taken for S dot type construction, so I just went to the next letter. So this is the U dot construction. And what I'm doing is this. So this, we're going to have UN of A. This is just going to be the set. Do I want to set? I guess I want to set. So it's the set of tuples A1 through AN. So just, that's the same n. So we just have n objects plus choices of sums for any contiguous subset. So by a contiguous, I mean I pick an I and a j and I sum them all up, and I need them all to sum. I don't need any subset. If you want, you can make a gamma space and make it any subset, but it's easier if you just take the contiguous ones. And then, you know, there's also a base point. I'm not going to worry about the base point too much. It's not going to matter. So then this is a simplicial set, and so D0 drops A1 and Dn. Well, I always forget these. Hang on. Yeah, I have. Di adds AI and AI plus 1, and Dn drops An. And when I say add, I mean using these sums that we've already chosen. We're not making any, you know, this way I don't need any conditions on strict associativity of plus or anything. This is like in the S dot constructions, you pre-choose all of your quotients, so you don't need to worry about compatibility of quotients. Here I'm pre-choosing all of my sums. And now I can iterate this. This is also, if you put in the morphisms, which I'm not going to spend the time doing, but if you put in the morphisms, you get another convenient addition category, and you can iterate this. And so you can say, okay, we can iterate this n times, and then we have m1 through mn indices now. And this is going to be a set of m1 by mn grids of objects plus choices.
Could you increase the distance between the blackboards by 10 centimeters?
No.
No.
The short answer is no, but I can rewrite this a bit lower.
Thank you.
This is the set of M1 by Mn grids of objects plus choices of sums for contiguous grids. And this is an n-simplicial object. And you can do the same thing in each of the directions. And again, because you've chosen all the sums, there's no worrying about associativity or anything like that happening. And now we can define a K-theory spectrum where we have, I'm actually going to ignore K0. You can just put in whatever you want in K0. But then we have the geometric realization of U dot of A, and then we have the geometric realization of U dot 2 of A, and so on and so forth. At the nth level, you have these n-dimensional grids. And traditionally, I just put the objects of A here. But regardless, it doesn't matter. This is going to be an omega spectrum above level 1, so whatever you want to do at level 1, you can make it an omega spectrum. At level 0, you can correct it easily, so I tend not to worry about it. So you can do this, and really, if you want to do this properly, you want to put in all the isomorphisms. Although you don't actually have to, because the U dot part will handle that for you. Oh no, this version doesn't. Okay, so I really should put the isomorphisms in, and I'll keep them there. So you say the two grids are isomorphic if you have, natural isomorphisms between all the data. And I also really want to point out this isn't actually a grid, or like this isn't actually a tuple, because what I did, I guess I'll do it down here. Let's say we have A1, A2, and A3. I've also chosen A1 plus A2, or a model of it. And I have these inclusions which are natural because of the structure of the category, because there's an initial object. And similarly, I have an A2 plus A3, and then I have an A1 plus A2 plus A3, and I have all of these structure maps between them. And now, again, if you've seen S-dot constructions, this should be looking far more similar to an S-dot construction, just with all the morphisms going towards the biggest object. So we have this. It's a spectrum. It gives you the direct sum K-theory of whatever A is. Sometimes for nice Waldhausen categories, you can take this category of cofibrations to be is a convenient addition category, and then you get this direct sum K-theory of that Waldhausen category. The nice thing about this U-dot construction is that for a lot of intents and purposes, it behaves just like the S-dot construction. So you can prove additivity, you can prove other things. In fact, just by taking the usual proofs for the S-dot construction and running them with U-dot instead of S-dot, and it works with very, very minor changes. So, so it's very nice that way. I also just want to put in a quick comment, just because a lot of people that I talk to don't seem to realize this. In the usual S-dot construction, W commutes with S-dot. You can take instead of your Waldhausen category, you can take a simplicial category where at level n you have n composable weak equivalences as your objects, and then that's a Waldhausen category, and you can do, but you can consider it as a Waldhausen category with only isomorphisms as the weak equivalences. So if you have a functorial construction which assumes that the weak equivalences are isomorphisms, you can do it for any Waldhausen category by replacing it with that simplicial category. So I'm only working in situations where you have isomorphisms, but you can actually very trivially put in weak equivalences if you want to by doing that kind of construction. So this, if you want the direct sum category of a Waldhausen category with non-isomorphism weak equivalences, you can do this exact same construction, but just putting in weak equivalences also. And it all works. Okay, so where's the filtration coming in? I'm going to cover that up and not worry about it. So each tuple and each grid has a maximal object, this sum of the entire grid. And in many nice situations, you can filter by, say the dimension of that object. And it'll give you a nice filtration on each of these U dots. And in fact, because the way that the structure maps work, actually, I'll draw out a structure map. The way that the structure maps in this spectrum work is that, say, I have A1, A2, A3. And I want to smash this with S1, and I want to map it to a grid. I can map it to grids that look like this. So we have we start with a bunch of zeros, and then somewhere we switch to A1s, and then we just put in zeros everywhere else. So we pick a row, and then I guess I should have really done it 3 by 3, whatever, it doesn't matter. So this is how you upgrade it to a grid, and the coordinate in S1 that you're doing, I guess I'll just do it this way. The coordinate in S1 that you're using tells you which of the 3 rows should be the one that's non-zero. So these are the structure maps. And so you can see that a structure map, if our largest object is the sum of these 3, then our structure map preserves that. Our face and degeneracy, well, I didn't tell you degeneracy, whatever, degeneracies are at a 0. But our face and degeneracies also preserve that because we're just adding 0, so we're not adding anything to the sum. So this is a well-defined filtration on the spectrum, and this is the Rognes stable rank filtration because each of the filtration levels gives you a subspectrum. So if I call that K of A, we can say, for instance, in the case, I don't know, when A is inner products or something like that, we can say that Fn of Ka is all simplices such that the dimension of the maximal object is less than or equal to n, and this will give me a subspectrum. And we can ask, what is the what's the nth filtered component? And this is one of the places that I think this is just ridiculously clever. Because it's the sort of observation that once you think about it very carefully is obvious, and before you think about it carefully is not obvious at all, which is my favorite kind. So I'm going to call this, so this is n, so that I'm going to call this, and I'll explain what this object is. This is K of S, K to the n, then you take the homotopy coinvariance by O n. So what is this? What's happening here? So here we look at the grids. So what things survive here? Here we have the grids where the maximal object has dimension equal to n. And if we have a grid like this, so let me give you an example. Let's suppose that n equals 3. And so I'm going to take the grid and I'm going to write down so here's a 3-length grid. Thinking of this as R3, and this is the vector and degree in dimension. This is the line along the x-axis, and this is the yz plane. So we have a grid like this, and we've chosen our maximal sum to be R3. And the key point about all of these structure maps is that they're actually inclusions. I said this is the x-axis, and this is the inclusion of the x-axis. This is the yz plane, and this is the inclusion of the yz plane. So this is a special grid in that these are all honestly sub-objects of R3. I could have taken this to be the z-axis, but then taken the inclusion to be mapped to the x-axis, which is totally fine. It's a totally reasonable object in our grids, but it's not a special object. Now, every object is isomorphic to a special object by saying, okay, we have our maximal object, which is R3, and then we're actually going to look at the images under all of the maps, and those are going to be our elements in the grid and our sums. And that's what our things are going to be, and everything is isomorphic to one of those. And then you just have to ask, okay, so we have that object, which is like this simplicial set of these kinds of objects, and then what are the isomorphisms that are left? Well, it's exactly the action of the automorphism group, which is ON. So this is the spectrum of these grids that I'm describing here, but it's actually a K-theory spectrum. This is why I wrote it as K of something, but it's K not of a convenient addition category, not of a Waldhausen category, it's K of a gamma space, and it's K of a gamma space which is not special, which usually means you don't want to use it because it's going to be bad. But luckily, we're actually just directly working with the simplices. I'm never going to need to say, oh, take this weak equivalence of gamma spaces and do something with it. I'm actually explicitly working with the simplices on the level of the construction, so it can't really be bad because I am doing everything directly on the level of simplices. So this is a gamma space. It's actually a gamma set. It makes life easier to think of it as a gamma set, and it's so this gives us a bunch of good structure on it. And by the way, I've said this as though it's only for inner product spaces. This will work for any convenient addition category, but what you need to first do is choose a sub-object structure. So you take your object and you fix a skeleton of the category of its sub-objects, and you say those are the good objects, and all the other objects must be isomorphic to one of these because we chose a skeleton, and then you can do this in general. It's just easier to visualize in a specific example, so I'm not going to worry about how you say this. How you say this rigorously for other convenient addition categories, I'm just going to vigorously wave my hands and say it's fine. Because it really is fine. Okay. So this is great. I think this is really nifty, just noticing. So here I'm also really using that of every dimension there's only one object, but it'll actually work equally well if there's multiple objects. You just need to take a wedge over every object, every isomorphism class, and they all separate out nicely. So this actually works in general. Here I'm using that. This is why I chose K to be square root closed, because I want all inner product spaces of the same dimension to be isomorphic. I don't want to deal with other things. But so this is great. But it doesn't actually tell us very much if we can't say anything about this. And so I want to talk about how you say something about this, which is a much more unusual object. And this is really, as I said, this part I think is very nifty, but everything else I'm going to talk about is, I think, just ridiculously clever. And I'm sorry, I do sound like I'm kissing up, but I really do really like this paper.
So far what you said is applying in this inner product spaces case, right?
Everything is going to apply in the inner product space.
Yeah, so I mean, you didn't define what this filtration is in that generality of this convenient addition.
No, so you need, I'm about to tell you what you're going to need, because I wanted to first talk about filtrations in a situation where they're obvious, and now I'm going to talk about filtrations in a bit more generality, and it'll apply to everything I've said so far. But I wanted to point out that it's when you know what your dimensions are, the filtration is very clear.
Thanks.
Okay, so I'm going to start with a filtration on a simplicial set. And I want to do a general filtration. I don't want to do a filtration by dimension, because filtration by dimension is a really rigid thing, and it doesn't apply in many situations. So I'm going to say that P is a poset, by which I mean it's a category where you have at most one morphism between any two objects, and also if there's a morphism from A to B and from B to A, then A and B are equal. There's only one representative of every object. You can probably do this with preorders, but it's more intuitive with posets. So I'm going to say, okay, so let's say poset X is a simplicial set. I'm going to need a slightly more general version, but let's start with a simplicial set. I'm going to do base pointed. Okay, so I can define the category of elements of X. And this has objects, pairs n x, where x is in xn. And the morphisms, I am 100% going to get the variance wrong if I don't cheat, so I'm cheating. So morphism mx ny is a morphism phi from n to m such that x of phi applied to x is y. Did I get this right or did I get it wrong? I think I might have gotten it wrong, even with my notes. No, this is correct. Good. So I wanted to be the case that a face maps to a simplex that it's a face of. So morphisms from smaller dimensional simplices to point to higher dimensional simplices. And so this is the category of elements. And then we're going to definition, a p valuation on x is a functor from the category of elements of x to p with a new initial object added. So this is a new initial object. Such that, so I call this new, such that the pre-image of the initial object is the base point. So we want the base point to sort of have dimension -1 or something like that, and everything else to have good, well-defined dimensions. If you think of p as like the positive, if you think of p as the non-negative integers, and this is the dimension filtration, then the idea is that the base point has dimension -1. Most of the time I'm going to be ignoring this part. It's not actually that important, but I wanted to get the definition correctly down. So this is a p valuation of x. This is assigning to every simplex a valuation. The valuation could just be, take the dimension. And this actually will work if instead of naively taking the dimension, if it's a degenerate simplex, you take the dimension of the thing that it's a degeneracy of. This gives you a proper valuation with values in integers. But now this is more general because this can be any poset, and things don't have to be comparable. And this induces a functor from p to pointed simplicial sets where we map p to the simplicial subset of those x such that nu of x is less than or equal to p. So where every element is sort of mapping to the subspace of that filtration level. And the thing to keep in mind is this is an example of a Grothendieck deconstruction, and it can really be done for any indexing category, not just delta. So this will also work for gamma sets, for instance, for general gamma sets, not necessarily special ones. And the other benefit of writing it this way is, I don't even know whether it's called, oh, and I forgot to say, because I'm a terrible collaborator, this is joint with Jonathan Campbell. I apologize. But anyway, proposition, lemma, fact, I guess I don't think it's even a lemma, it's a fact. This factors through to K-theory. In the following sense, you can say, okay, like if X is, a convenient addition category, we can also write down such a functor for just a functor from a convenient addition category to a poset in this way, where we say that 0 has to map to this initial object, and then we can say, okay, so now when we're building this K-theory, you have simplicial sets, and you can use the valuation on the convenient addition category to produce a valuation on each simplicial set. And because the structure maps are actually going to be compatible with the valuation, because things are functorial, it will pass through to K-theory, and you will get, instead of a functor from P to simplicial, P plus to simplicial sets, you'll get one from P to spectra, which will give you the subspectra, which are the filtered parts. So the nice thing about writing it down like this is that you write it down and then it works at any level that you want it to work at, it will work. And so now we can say, okay, so that SKN is a gamma set. And I'm actually going to describe the gamma set. So SKN, this is the gamma set. So gamma set is a functor from finite pointed sets to sets. Actually, in this case, we're doing pointed sets, but it doesn't really matter. And what you do is you map n to sets of n tuples of things such that their sum is exactly whatever we're doing, is k to the, oh, sorry, I'm reusing m, I guess I use m. You map m to m tuples that add up to your thing, but now they're not ordered, these are sets. And these are actually, this direct sum is as subspaces of Kn, and all of these must actually be subspaces of Kn. Not things isomorphic, but actually subspaces with the subspace data. And in the more general convenient addition category, you have your subspace structure, and you have to be choosing objects in your subspace structure as opposed to just general objects. But once you have that, this is actually a gamma set, because these no longer have automorphisms, because no two can be isomorphic without acting on Kn non-trivially. You can't actually move them around at all. So this is an honest gamma set. You don't, all of the isomorphism structure has now gone into here, so we're just working with a gamma set. Again, not special at all. Keep that in mind. At level 1, you just have the set, the singleton set containing k to the n. You can't add k to the n to itself in any way. This is not special, but it still has a k theory. It's fine. So what is this k theory? Guess maybe this deserves theorem.
Somehow you made the shell.
I really tried putting, I don't know. Maybe I needed the momentum to shove them apart rather than,
Just yank it off all the way.
yeah, and I'll throw it into the audience. Yeah, would not be useful or good or, possible. So, I guess maybe this should deserve theorem. Although really, I'm going to put Rognes here, because this is really based on stuff in the paper that you should all read, because it's great. So this K theory of this, again, because I'm doing it for inner product spaces, but as I said, this works in general. This is the suspension spectrum of the suspension of the nerve of this category of decompositions. So this is the decomposition category. Where the objects are sets A1 through AM of non-zero subspaces such that A1 plus AM is k to the n. And my morphisms are under refinement. So I'm going to say that a morphism from A1 through AM to B1 through B, oh no, I need a letter, L. So it's a map F from the set 1 through L to the set 1 through M, such that the direct sum over the pre-image of anything is, B I is AJ. So the idea is we're taking each component of this set, and we're possibly decomposing it into a further decomposition, and all of them have to be non-zero. But we also need to make sure that m is not equal to 1. That's what this circle here means. If we allow no circle, then this has an initial object, and then its homotopy type is not terribly interesting, and also the theorem is false. But if you remove it, then suddenly it becomes very interesting. And so each of these is a suspension spectrum of a space like this. And we know that this space, I can tell you what its dimension is, because it's a poset with nice levels counting by how many things there are, and the smallest one have 2 objects, and the largest one has n objects where you're decomposing into lines. And so this has dimension n, oh, I already wrote this. This has dimension n minus 2, and so the suspension has dimension n minus 1. And I guess I'll cite Sander for this one because he proved a very general form of this, which is that the nerve of this decomposition category is weakly equivalent to a wedge of spheres. So this is a standard thing for Steinberg modules. It's a standard result in many other situations, but it's also in particular a situation here, and also in general if you're working with free R modules, and also if you're doing finite sets, and also if you're doing lots and lots and lots of other nice situations where you have these kinds of dimensional things.
So this is just one building. I mean,
I'm going to say something about the proof in a second. Was that the question?
No, but it's like this decomposition. It is like if you have an E1 algebra, it shows up in stability, which I guess is.
Yes, it's the same. It's the same type of result.
But they are. But what are the hypotheses of the? But this is in for something coming from.
So this is currently in inner product spaces. So if you're working with inner product spaces, this is the decomposition category for inner product spaces. If you're working in a general convenient addition category, it works in a general convenient addition category. This part, but this part is you need more assumptions than just a general. So this I guess I'll put that A is inner product k to the n, but here this is much more. This is true always.
Can I check? And
yeah.
Can you pick the unbased suspension? Or
So everything is based. Well,
sorry.
yeah, no. I'm trying to decide how I want to correctly write this down. I guess.
I think it is an unbased suspension. It's saying there are 2 cones.
Yeah, there are 2 cones. It's so the point is it's an unbased suspension. Then you pick a base point to do the rest, and it doesn't matter which one you take. But so I agree. This makes me very uncomfortable. I have to say, every time I have done this, I'm like, this is just wrong, but it also is absolutely how it works. So this is one of these places where I'm like, but as far as I can tell, this is just the correct way of doing it. Because you end up with the join of 2 spaces, and it's not the reduced join, it's the honest join. And neither of the spaces is, well, one of the spaces is kind of pointed, but the other one isn't. So is that the base point you take? I don't know, maybe. But it's, I'll show you. So how do you prove this? Where does this come from? Well, the point is that this gamma space has a filtration, has a valuation with values in this poset. This is clearly, by the way, a poset. This is, by the way, why a convenient addition category inclusions have to be disjoint, because if they're not, then this is not a poset. But we made that assumption, so this is a poset, and I'm going to give you a filtration on this gamma set, and all I'm going to do is I'm going to take the tuples of subspaces the sets of subspaces, and I'm going to send it to, these are actually multisets. You're allowed to repeat zeros, not anything else, obviously, because you need the direct sum to be k to the n, but you're allowed to repeat 0 if you want. And all I'm going to do for this gamma set is I'm going to map A1 through AM, and I'm going to map it to the subset of non-zero terms. So that gives you, and you can check that. So how does the K-theory of a gamma set work? Well, a gamma set is a functor from finite pointed sets, I guess I called it SA, to I'm doing everything base pointed, so I forgot the base point. To pointed sets. And I have a functor from delta op to finite pointed sets given by Sn pointed. And I'm really thinking of Sn as S1, wedge S1, wedge, smash S1 n times. So then we take this composition and we get a simplicial set. And that's our nth space of the spectrum. And the fact that I've written down this functor sort of from subsets of these kinds of subsets to this means that this composition, because that's where SA lands, you can map it down to this poset, and you can check, it will give you a filtration on this. And the idea is that we're going to figure out what the filtered quotients are of this filtration, and we're going to use that to analyze this. Okay, so how are we going to analyze this? So we need a couple of facts. So the first fact, which I'm going to label fact, which, if somebody knows a reference for this, I would really appreciate this, because I'm sure that everybody knows it, but I couldn't actually find it to cite, which was frustrating. It says the following, that we have that the homotopy colimit over P and P of FP, this is really anything, but I guess I'm thinking about this one, so I'm going to do this one, is exactly the original thing back. Which is as it should be. You have a homotopy, you have, a filtration, the union of all the filtration components should be the original thing, and this is what that is saying. On the other hand, we can analyze this homotopy colimit in a different way. We're going to map it in the following way. We're going to say, okay, we have this FP, and I'm going to focus on the nth level. So homotopy colimits of spectra are level-wise, so I'm going to look at it at each level. And I'm going to map it to the homotopy colimit of the following functor, which is, I guess I'll call it G. I'm going to define G of P to be Sn if P is Kn, and I'm going to have it be a point otherwise. And there's a natural transformation between these, Sn. So what's happening here the first key is that Fkn of K of Skn, this is the lowest level of the filtration. Well, what is this going to be? This has to be, you look at grids, you know, m-dimensional grids, and in each one of the elements has to be equal to k to the n, and all the other elements have to be 0. So all you're really choosing is choosing a point in your grid, and the simplicial set of all possible grids is exactly Sm. So this is actually equal to Sm. That's the lowest level of the filtration. If you take F(A1) through Am of this, oh, I should not use L, Kn at level m, this is going to be Sm times L. Because now each of these has to go into a grid point, but they're all independent. Because I say it has to be less than or equal to this, which means that you're allowed to put two of them in the same box and add them. And so it's just you're picking a point in your grid for every one of these, and that's just, well, the product of a bunch of these. So that's this. So the point is that this map is 2m minus 1 connected at each key. Because here it's just at the lowest level it's an isomorphism, and everywhere else it's going from a tight enough dimensional sphere to a point. And so as maps of spectra, this is going to be weak equivalence of spectra. So this induces weak equivalence of spectra because it's 2n minus 1 connected at level m. Okay, so I mean, if I can't compute this, then this doesn't help. But we can compute this, and this is the place where I think it's really cool. Whenever you have, so I guess I'll call this a lemma. So if you have C, which has an initial object, and we're going to let C op be the subcategory of all non-initial objects, and we have a functor G from C to spectra, which is where G of 0 is something called Y, and G of the initial object and G of everything else is contractible. Then this homotopy the homotopy colimit over C of G is exactly that thing that I wrote. And this works for any category. And the nifty thing about this is that you do it by explicitly writing down the oh, sorry, no, it's I want nerve and Y. I want Y just the nerve of C, and in particular, if Y is the sphere spectrum, then you get what I wrote down before. And you do it by, right, again, I kind of feel like I should put Rognes here, even though this doesn't actually technically appear there. You do it by writing down the bisimplicial set at each level, writing down, and then you see that it's exactly this space at every level, which I thought was really cool. Like you just see all the simplices coming together to form this. So I thought that was very exciting. Okay, I'm going on to the end. So we have, did I erase it? I think I erased it. Oh well, we had the result. That was really cool. No, it's up there. Okay, good. We have that. And so these decomposition spaces, they're not just general spaces, they're really spherical spaces, which means that all of the difficulties in taking their homotopy coinvariants go away because a lot of the, if you're working homologically, say, because a lot of the homology is 0. And say if you're working with rational coefficients, which is really the only case that I care about, then really you're working homologically, and you get some really cool stuff. I'm going to say one of the things, and then I'm going to stop. Oh, I wanted to make a quick comment. For a general convenient addition category, you start with a filtration on the convenient addition category, and you can filter by that, and you get the same kind of results about its splitting as homotopy coinvariance. And then you take these decomposition categories for each individual object in your convenient addition category, and this works in generality. And the hard part then becomes proving the sphericity result that we have for these examples. Because in general, this is not going to be true. You take a general way of decomposing things, you're not going to get a bunch of spheres. Yes?
In the lemma, do you maybe have to assume that C is a strict initial object? Like there's no maps from any other object? If a object maps to an initial
yes,
object,
sorry, I forgot to add, this is a cosiv. You're right.
I think the same.
Yes, you're right. So if it's C has to be a cosiv, and then C open has to be a cosiv, and then it works. And in fact, you don't actually need the initial object. You just need C to be contractible, and you need all of the places. You pick any functor, and you take all the places where it's not a point, and that's the that needs to be the sieve part, and then it works. I mean, then you need a little bit, another mild assumption, but I was mostly writing it down for this particular case. Okay, so in general, so again, for inner product spaces, although this also works for rings, you get this spectral sequence. I'm gonna get wrong if I don't copy it from my notes. No, where is it? There it is. Actually, well, wait, where? There it is. Okay, good. So we have H1 of O1 of K with coefficients. So I'm going to call dec n. It's going to be the n minus second homology of, I want the n minus first homology of this decomposition thing for K to the n plus 1. And no, yes, no, K to the n, and n minus 2. And now that's correct. And everything was with rational coefficients. And H1 of O2K, dec 2, so on and so forth. And then you have H2 of O1K, dec 1, H2 of O2K. No, what am I doing? No, that's correct. Dec 2. And so on and so forth, with the homology going up vertically and the interior dimensions going up horizontally. This is D1. This is the E1 page. And as it's written right now, it's just a first quadrant spectral sequence. There's no immediate degeneration anywhere. But if K is infinite, then it's known that this disappears below, that everything here and below is 0 if K is infinite. And so, except for this one, which is Z or Q, whichever. And so you get these complexes which are growing slowly, and on their face these are not motivic complexes because they have a different formula. Sander thinks that they're going to be isomorphic to motivic complexes, but we tried to show that at this level here, where we have H3 of O1K, back one, I might be off by one, I'm sorry, and then we have H2 of, H3 of O2K, deck 2. I think I'm off by one, but yes, these should be zeros. Why
So
am I-
is this now computing the associated grids?
Mhm.
Okay, nice.
This is putting all of the results back together to the original K theory. So this is the thing for the orthogonal groups, which is just generally not known, and I don't know how to compute these. And if somebody wants to talk to me about how to compute things, I would be very happy. But I haven't been able to do it. But you get the same thing if you put a ring in here, and if you just take general R modules, if it's a nice enough ring, or if you take a general field, you can do, vector spaces and do standard K theory. And then this should really give you motivic complexes. But we can't prove it. Sander thinks it's true, which I guess is an indication that it might be true. But Jonathan and I sat down and tried to prove that this one for a general field with modules is going to be the same as the standard one. And so far we have failed utterly, and we've been working on this since 2021. So I've slightly written this off as I'm not going to be able to do it. Maybe somebody's way smarter than I am or way better at computation, which is not hard, will be able to do it, but I couldn't do it. So maybe it's trivial and we just didn't see something, and if you could figure it out, I would love to hear it. But I really like that you get these nice complexes and that they're often the right length, though in general for the orthogonal case we don't even know that. I would love to know that, and maybe at some point this can tell us something about what orthogonal K theory actually looks like beyond it definitely has this kind of filtration on it. So thank you for listening.
Questions? Start from the far end, maybe.
Okay.
So if you can compute some of this, will this allow you to compute the homology of GLN?
If you could compute these, then yes, but I'm not sure. I don't know how to compute them. I'm not sure you could do anything. I don't think this technology is better than the existing technology. It's just slightly different and works in, or the orthogonal case, which the other one does not. Oh, sorry, one quick comment. You can extend this to Waldhausen categories to get the original result from Rognes's paper back with a different type, with a more complicated type of decomposition, and then you get a different space, which is 2n-2 dimensional, which is instead of n-1 dimensional, which is what it ought to be. Anyway, apologies.
No. Yeah. So does scissors congruence K theory fit into this framework?
No, it doesn't, unfortunately. Or rather, it does. And I've been trying to write down, you can do the filtration by volume, and then you're looking at all decompositions of a particular volume.
Oh.
But, yeah, right, exactly. I was like, I can't do anything with this. You can write it down, but also I don't know how to do continuous filtrations properly. That's
persistence module.
Yeah, it's in theory, this will totally work. But in practice, I have no idea how to get anything at all out of this. My hope is that, what ought to happen, morally speaking, is that these should somehow be related to scissors congruence. And, oh, you took a dimension filtration, you got some good complexes, and those complexes should be scissors congruence mumble something, in theory. I don't know, I haven't tried that. That sounds like a lot of fun, but I have no idea.
And so I gave some lectures on this in Bergen in 2010, which has been on some web pages for a while, and then I guess work with Coopers and relations and so on was referring to it, so it's also on the archive by now. So the So if you do this for algebraic K theory of, in the case of a field, the rationally the E2 term is Morava K Milnor K theory,
Mm-hmm.
which is the same then as motivic cohomology in the left-hand column here.
Mm-hmm. You get that same thing here.
So you get the differential induces the Steinberg derivation.
No, we don't know that. You get
No,
the
but I mean,
correct thing in the
it
left.
does.
In
I
your
know-
case, but in this case,
Oh,
I'm
sorry,
not sure.
okay,
Yeah.
In the case where you're doing the rank coefficient algebraic K theory of fields, it fits with motivic cohomology in the bottom in that column, and these connectivity results are then basically equivalent to the Soleil gradient and vanishing conjecture. So they're basically the obstruction to getting mixed state or mixed charge motives in as a model for general fields involves the fact that motivic we don't know that that negative motivic homology is rationally trivial, and that's equivalent to the vanishing of the things below this line here. So if you could prove that this was the same as motivic homology, you would have proven invariance and Soleil vanishing conjecture, and a lot of people would have been very happy.
Right, but I wasn't trying to do that. I was just trying to prove that map
In your orthogonal situation.
in the orthogonals. No, in the non-orthogonal situation, but with the decomposition complexes instead of with your common basis complex.
Any other questions? Right, well, thank you very much.